Every morning follows a digital trail. You pay for a coffee with an app, check into a class, or update your ID. These simple actions create millions of data points every single second. With that much information moving at once, it seems impossible for a global app to remember your specific order from years ago. It has to distinguish your history from millions of other users without ever mixing up the details. To manage this, architects rely on a precise blueprint. This architecture is drafted long before anyone writes a single line of code. Without this pre-planned structure, the data would be a static noise of numbers. Organized architecture is the only thing that allows a system to handle the complexity of the real world. Architects map out this world using an entity relationship diagram. It's a visual shorthand that turns real-life subjects into a logical map. We start with the subjects of our database. An entity lives inside a rectangle. To describe it, attributes like a name or phone number branch out inside ovals. But we need a unique label, the primary key, like a customer ID, to ensure it's always found. Turning complex people and objects into these simple rectangles and ovals is the foundation of digital order. Data becomes useful when these subjects interact. When a customer places an order, we represent that connection with a diamond. This shape tracks the relationship between subjects. These connections follow strict rules, called cardinality, defining exactly how many times subjects can link together. Some links are one-to-one. For every one person, there is exactly one unique ID card. The system ensures that one card can't belong to two people. Most connections are one-to-many. A single customer can place many different orders over time, but each specific order belongs to one person. We also see many-to-many networks. In a university, many different students are enrolled in many different courses at once. Setting these rules on the blueprint prevents errors once the system is live. It makes it impossible for the database to assign your purchase to the wrong person. Engineers spent years refining how to physically store these links inside a computer. Early systems used a tree-like structure. Information flowed from one parent down to several children. It was organized, but it was too rigid. If a child needed a second parent, the system couldn't handle it. Next came the web structure, which allowed subjects to link to anything in any direction. But without a central trunk, the data often became a tangled, messy spiderweb that was difficult to manage. Today, we use the relational model. It organizes everything into clean, separate grids. Instead of drawing complex webs of lines, it uses matching data to bridge the gaps between tables. This grid system is now the standard. It provides the clear structure of a tree while allowing the complex, overlapping connections of a web. Even with these grids, we still need a way to link two separate tables. Imagine a customer table and an orders table side by side. On their own, the order doesn't know who bought it. To bridge them, we copy the customer's unique ID and drop it into a new column in the orders table. This is the foreign key. That copied ID acts as a digital name tag. It gives the database a permanent way to look at any order and instantly find the exact person it belongs to. These foreign keys are the real-world version of the diamonds we drew on our blueprint. They are the glue that holds the digital world together. Massive, complex databases are actually quite simple. They are just rectangles, ovals, and diamonds working together. This system translates human logic, the story of who bought what and where it went, into organized, searchable tables. Database design isn't just about memorizing code.